In the final section of Chapter 2, Section 2.7, we're going to be solving problems involving more than one right triangle. So in this question, we are asked to calculate the length of side length CD to the nearest tenth of a centimeter. So we're looking for this side length right here. And if we notice in this problem, there are two right triangles. While in triangle BCD, all I have is an angle. So I do not have enough information to find side length CD when I only have an angle. I need another side of that triangle. Well, if you look, the side that's common to both these triangles is side BD. And I do have enough information using triangle ABE to find side length BD. So I'm going to accurately label. I'm using triangle ABD to begin with. And I want to find side BD, which is really little a if I'm looking at triangle ABD. So I know angle B, which is 47. I know the opposite side, and I'm looking for the hypotenuse. So I'm going to be using the sine of 47 degrees is going to be the opposite side, which is 4.2 divided by, and I'm going to use line segment BD now instead of side A because I'm going to apply BD to the second triangle in the next step. Again, isolating side BD, I'm going to end up getting 4.2 divided by the sine of 47 degrees. And if you're unsure how we isolated BD, you can go back to some of the earlier videos where we showed the steps for that. Now getting out your calculator, 4.2 divided by the sine of 47 works out to be that BD is equal to 5.7 centimeters. So now I know that this length is 5.7 centimeters. Now I have enough information in triangle D or BCD to find side length CD. So now I'll just switch colors. And now we're looking at triangle BCD. And I have an angle which is 26. I want to find the adjacent side. I know the hypotenuse. So therefore, I'm going to be using the cosine of 26 degrees is going to equal the adjacent side, which is CD, over the hypotenuse, which is 5.7. And now multiplying both sides by 5.7. And if you multiply the right side by 5.7, it will cancel out with the denominator of 5.7. So now I just get out my calculator and again calculate 5.7 times the cosine of 26. And that works out to be 5.1 centimeters would be my final answer for side length CD. So you can see that in this problem, it was a two-step process. You had to find a piece of information from the first triangle and use that in the second triangle to find the desired length of line segment CD. Okay, I want you to pause the video and give this one a turn. Okay, in this example, I hope you had a chance to try it. We are asking to find side length XY, and again, in the small triangle on the left, I only have one angle, so I need to find some other information. And the side that is shared by both triangles is side YW, so that's the side I'm going to have to find first. So first of all, I'm dealing with triangle WYZ, and I want to find this side length right here, which is WY. And that side length is opposite of the angle of 20 degrees, and 8.4 is the hypotenuse. So therefore, I'm going to use the sine of 20 degrees. It's going to be equal to WY divided by 8.4. Again, I'm going to multiply both sides by 8.4. And that will leave me with side length WY. So getting out your calculator, 8.4 times the sine of 20 works out to be 2.9 centimeters. Is going to be side length WY. So now I know that this is 2.9 centimeters. So now I have enough information to figure out side XY. So in triangle, now I'm dealing with triangle WXY. Okay, I know angle 22. 2.9 is adjacent. I'm looking for the hypotenuse. So again, the cosine of 22 degrees is going to be 2.9, which is the adjacent, over xy, which is the hypotenuse. Again, isolating xy, it's going to be 2.9 divided by the cos of 22 degrees. So 2.9 divided by cos 22. This side length xy, if I round off to the nearest tenth of a centimeter, is 3.1 centimeters. In our next example, we are looking at a word problem, and it says from the top of a 20-meter high building, a surveyor measured the angle of elevation of the top of another building and the angle of depression of the base of that building. The surveyor sketched this plan for her measurements, determined the height of the taller building to the nearest tenth of a meter. Now, I'm going to give you a couple of angles here. First of all, we're going to say that the angle of elevation, okay, it's not given in the problem, is 30 degrees. And the angle of depression is given at 15 degrees. Okay, so now we're going to have to, first of all, draw a diagram of this situation. So we have a small building, and we have a taller building. And it tells us that the height of the smaller building is 20 meters. And it says the angle of incline to the top of the other building is equal to 30 degrees. So here's my horizontal, and the angle of incline up here is 30 degrees. It also says the angle of depression from the smaller building to the base of the big building is 15. So that means, again, angle of depression, there's my horizontal, that means that this angle here is 15 degrees. So now the goal is to figure out the height of this entire building. Well, notice we have two right triangles. We have a small one down here, and we have a larger one down here. And if I can figure out this segment of the top right triangle and this segment of the bottom right triangle, add them together, I'll have the height of the entire building. Now, if this height of the smaller building is 20, that means that this side length here is also 20. So we know the bottom half of the height of that building. So now, just like before, I need to calculate this piece up here. And the only way I can calculate that piece up here is to figure out the length of that shared side. So let's first of all label this. So let's label this vertex A, and this one B, and this top C, so we have some reference points. And we want to figure out, first of all, the length of AB. I'll call this guy down here D. So first of all, I'm dealing with triangle ABD, and I know an angle 15. I know the side opposite is 20. I'm looking for the adjacent side. So therefore, the tan of 15 degrees is going to be the opposite side, which is 20 divided by line segment AB. And therefore, AB, if I do some manipulating, is going to be the tan, 20 divided by the tan of 15 degrees. And if we calculate that, that works out to be 74.6 meters. So that's going to be this length right here, so 74.6. So now I want to use my angle of 30 with this length here to calculate BC. So now I'm dealing with triangle ABC. And I know an angle of 30. I want to find the opposite. I know the adjacent. So again, I'm going to use tangent. So the tangent of 30 is going to be the opposite side divided by 74.6. And now multiplying both sides by 74.6. I'm going to have 74.6 times the tan of 30. And that works out to be 43.1 meters is BC. Now you have to be careful because we're not quite done. problem yet. We want to figure out the total height of the building. So I know that this point apart, is 43.1, and I also have 20 down here. So to find the height of the taller building, I have to take 43.1 meters and add 20 meters. So that equals 63.1 meters. So we would just write our statement saying the height of the taller building is approximately 63.1 meters. Okay, so there's an application of the same type of questions we did in the first two examples and ones that you will see on future assessments. Okay, the next section on using right triangles in 3D, due to LeBlanc scheduling, we're gonna just leave that section out. So here is your assignment. Omit the green questions because those are for the three-dimensional problems which we didn't do. So here are the questions I'd like you to try. Again, check your answers on the website as the full version of the answer key is provided there for you. All right, good luck.